did I email you that I had put all of the videos from summer? Okay, yes. I mean, for your entertainment, I don't know that they're very useful, but yeah, we were just, you know what it was like during COVID. You're just hanging on by a thread, trying to, yeah. So that was the outgrowth of COVID, at least for me. I was like, you know what? Let's do what we can to make it entertaining. So if that's useful to you, great. If not, you know, whatever. I don't know. Maybe you'd like those more than coming to class. But here we are. Okay, so we're going to be doing some substitutions. And so the idea here is just there's a couple of different places where there's some ways that you can substitute, make some substitutions like a U substitution. You're familiar with this. That will allow us to solve some differential equations that heretofore we couldn't solve. So it's sort of like adding integrating factors. This is just another technique. So the idea here, there's just two that I want to go over today. There's a few others, but I don't care about them. This one is the idea behind this is that if you have a particular differential equation, and if that differential equation is what we call homogeneous, then we can actually modify it to be separable, which you know how easy it is to solve separable differential equations. They're the easiest thing in the book. And so just as a lead up to this, if you have a particular differential equation and you have this substitution, the idea is we're going to use the chain rule. And right now you're like, well, what is this substitution? Well, we'll get there in a second. But the idea here is that we're going to take the chain rule from multivariable calculus, and because this is a function of two variables, so here's the substitution. Use this chain rule to rewrite dy over dx and give you this thing over here. And if we do it in a clever way, what happens is that your differential equation becomes separable. So that's the trick here. But I'll show you exactly what way we want to do this. So to understand, let's see, I have too many words. Why do I have so many words? Hold on a minute. Yeah, there's way too many words, but we're just going to go with it. Okay. So this homogeneous, I thought I deleted some of these words, but there they are. Okay, so homogeneous. Homogeneous differential equations are the ones that we're going to be solving using this method, at least this particular substitution. And so here's what's meant by homogeneous. Homogeneous is a differential equation. Here's one way to think of it, is that the powers of the variables, so you look at this and you think, oh, is that like an exact, it's sort of in the same form as an exact differential equation. But the key here is that the powers of all the variables are the same. That's what homogeneous means. And there's all of these words down here, but really it all boils down to the fact that we have all the same powers. Let me show you an example that'll help sort of illuminate this. So here's an example here. Notice that all of the powers are degree 1. So you got x, degree 1, y there, degree 1, and the x there times dy. Everything's degree 1. Just to show you oh, yeah, I don't have anything good. Oh, I picked boring ones. Nothing interesting. Here, I'll make up another example just to illustrate the point. Here's another one, and you're going to say, wait a minute, the powers aren't all 3. I'm going to make one with all 3's. So here, I'll do it like this. Let's do it this way. So dy over dx, just a minute. I moved the little thing because I was typing in numerical methods, but this is better. So dy over dx is equal to, let's do this, 3x cubed plus xy squared over 6y cubed plus x squared y. Yeah, that one works. So that is also homogeneous. So here's how you tell that these are both homogeneous. So first off, with the second one looks a little different from the first one. We want to write it like that. You notice that one, it looks like in the same form as your exact equations. So let's just go do the cross multiplying. That's the easiest way to do this. So cross multiply, you have 6y cubed plus x squared y times dy is equal to 3x cubed plus xy squared times dx. I should really switch over to notability at this point, but I won't yet, but I will see. And then the final step, let's move everything to the left. So we have 6y cubed plus x squared y times dy. I guess I'll put this out here, negative 3x cubed plus xy squared dx. Ugh, that's terrible. There it is. Okay, let me back up for just a sec so that you can, I know that you're looking at this saying, well, maybe some of you have caught on, but unlike this, here all of the powers are 1. It's degree 1, 1, 1, 1. Here I have a cube, I have a square, I have a power of 1. So it's like, wait a minute, I thought you said, well, here's the thing, is that when I say that the powers are all the same, I'm really most concerned with the way that the variables interact with one another. And so that's where all of this comes in down here. So the way you check, and actually I never put a t in there, I just look at it. I'll explain in a sec. But the way you should, at least the book way to do it, is you plug tx and ty in for x and y. And as long as you can factor out t to some power, then we're all happy. So here, let me go back to that example that I just wrote in big, bold, red ink. And now I think I'm sick of looking at the PowerPoint, and I'm going to get this on Notability. So bear with me for a sec. Copy and delete. Let's go over here. Okay, that's better. Okay, so let's use the book definition, and then I'll tell you the easy way to do it. So the book definition is you would take this, and this is im. So here's im. This is in. And you're going to plug tx everywhere you see an x and ty everywhere you see a y. So here the im becomes, let's see, this will be negative 3 times t cubed x cubed plus tx plus, not plus, times t squared y squared. I think that's it, right? Yeah, so I've replaced the x with tx and the y with ty. And notice that if I do that, I can actually factor out t cubed. So then you're left with 3x cubed plus xy squared. So I think some of you are catching on that what I mean by the same power is if you think of the number of variables that have been multiplied together. So here you have 3 x's, x. Here you have an x and 2 y's. There's 3 variables, x, y, y. So that and this have the same power. And we want to make sure that the same is true over here, and it's the same power as the other one. So you can see now that there are 3 y's, and then there's 2 x's and a y. Everything has a power of 3. And we could do the same trick as we do down here, but we aren't going to. Okay, so as long as that's true, here's the substitution that you're going to do. Once I find it here, there. Okay. So once you determine that that's the case, you can either use this substitution, y is equal to u times x, or x is equal to v times y. I don't like v. V looks ugly. It gets confusing to me. So I always do this. But you can do it this way. It just depends on which way it looks. It looks like it'll be easier. So either way you do it is fine. Bear in mind that what's going to happen is you're going to end up making the dy over dx is going to be the harder of the substitutions, but we can do this nonetheless. So let's see if we can do this here, just as an example. So this particular differential equation, we're going to, what is this? Oh, yeah. Oh, no, this is wrong type of differential equation. That's a Bernoulli. We'll get that in a minute. Where's my substitution? It's here somewhere. Okay, let's just go over here. We'll just do it with this. Let me clear my ink. Oh, it won't clear. Come on. Just a minute. I'm going to have to exit out. Discard. We'll pull it back up. Okay, so we'll do this one, nice easy one. First of all, we check, is this one that we could use this, is this homogeneous? And so you check here that everything is degree 1. And here, everything, all of the terms are degree 1. So that's sort of the easier way to do it than putting t's in and trying to factor out the t. But if you had put t into this, that is, change the x to tx and the y to ty, you would factor out 1t. And here, if you put x equals tx and y equals ty, you would factor out t. So that's why those are degree 1. So let's go ahead and try this out. We're going to use y is equal to u times x as our substitution. And what that's going to do for us is, what is it going to do for us? It's going to be dy over dx is equal to du over dx times dx. Just a minute. That doesn't make any sense. Hold on a sec. Let me back up here. Whoops, that was too far. Come on, buddy. I hate PowerPoint on the iPad. Okay, let me try again. So y is equal to u times x. Let me just go back and make sure I'm doing this right. That's Bernoulli. Okay, yeah, there it is. There, I just didn't. There's the dy. Okay, so y is u times x, and we're going to use this, the whole thing about the chain rule in multivariable calculus that says that dy now is going to be u times dx plus x times du. Okay, just have to be reminded. U times, so let's see, dy is u dx plus x du. Kind of makes sense. Now let's just go blindly make these, I mean, it feels like it's blind, but it's not. We're going to just go ahead and make those substitutions and see what happens. So you have x times ux, or x minus ux times dx plus x times u dx plus x du. There we go. Now it feels better to me. So that all went here. And that equals 0. Now the cool thing about this is that it looks like things are getting worse, but what we're going to end up with is separable. That's the cool thing about doing it this way. Let's see. Let's see if this is the case. So let's see, over here I've got x times 1 minus u dx plus xu dx plus x squared du. And of course, because PowerPoint doesn't let me scroll, I'm running out of room yet again. So give me a sec. Delete. Just switch over here. Let me just put this in here. That's much better. Sort of. So far, so good. And now, yeah, I promise you that this is separable, but I'm going to work it through anyway. So this is x dx minus, oh, no. Sorry, what am I doing? I'm unseparating. So x times 1 minus u dx plus, let me just factor out the dx, plus xu dx. There, that's better. Okay, now I don't know if you noticed this, but let's do a little bit more math here. Yeah, I guess that this was dumb of me to, that's better. I wasn't sure if that 1 minus u would get factored out and divided. Okay, now those go away. And so you just have x dx plus x squared du is equal to 0. And now I don't care what side I put this on. Let's put it on the, I don't know, move something. I don't care what. X dx is equal to negative x squared du. And then you're going to get x over x squared. This is overkill because you all know what's about to happen. 1 over x dx is equal to negative 1 du. Now this is, it's been, basically I've separated the variables. I have only x's here, I have only u's here, and you can do your do your integral. There, all done. So 1 over x, easy, natural log of x. Easy, negative u plus the constant. And then the only thing that you have to worry about now is going back and substituting what is u. Well, here is y, so that means u is y over x. So let's go ahead and plug that in. Natural log of x is equal to negative y over x plus c. You could solve that for y if you needed to, but that pretty much has done it. All right, well, let's see. I don't know, do you have any questions about how that worked before we go and look at another one? This is the key. And so, but it can be reconstructed if you recognize that you're just going to make that substitution and then take the differentials. Well, let's go grab the other example here. So here's the second example. It's similarly boring. I suppose I could have, well, yeah, you'll have less boring ones on your homework, which means we'll have plenty of time to discuss them on Wednesday. But go ahead and give it a go here. See if you can, by the way, I'll just tell you right now that this is homogeneous. So you'll be able to separate it the way that you want to. I'll get it started, I suppose. So y plus 3x times dy minus 3y plus x dx is equal to 0. So there it is. Homogeneous, you can see all of the powers here are linear, and all of these are linear. So everything's in good shape here for this. So go ahead and make your substitution. I mean, you have the two choices, but you know which side I'm going to fall on. I'm going to do this. There might be reasons to do it the other way. You know, if the function would be simpler, but I don't know that I don't know that I've ever had an issue like that. I'm just going to paste it in here. There we go. There. Yeah, feel free to work with a friend. I know you don't want to talk because it's math class. But I'll put these stickers over here in case if you have regrets. If you want to get the little, did anyone take baby Jesus yet? Oh, yeah, so they did. Nice. There. Nice. Both baby Jesuses. And it's still there. Oh, I should pick random people. That'd be much more fun. I just realized. Yeah. Oh, he's not here. All right, well, let's go ahead and see if we can work through this. It really isn't all that tough. Once you realize that this is the way we're doing this, you're just gonna make that substitution, and it magically works. So let's go ahead and give it a go. So let me set it up, and then we'll see if we can bring some other people to go ahead and help me out with a couple of the parts here. So we've got ux plus 3x times dy. Oh, dy is changing as well, isn't it? U dx plus x du, 3ux x plus x dx. There. How's that? All right, I guess I'll just go ahead and crank through this a little bit. So FOIL. X squared u du, x squared du, 3ux dx, plus, minus, rookie mistake, x dx. So I've just multiplied. Got to collect all the dx's together. Ooh, do I get to cancel? Oh, joy. That's always exciting. Is there anything else? I don't see anything else cancel. Okay. What's wrong? That's it? Okay, so I guess, though, I can move the x's to the right. So let's do that. So I've got x dx minus u squared x dx on the right. And then what's left on the left? Oh, wait, I left. What just happened? Didn't this cancel? Okay. And then on the right, or on the left, I've got x squared u plus 3x squared du. There we go. Did I get that right? Does that look okay? Yeah, don't worry. I've got the randomizer fired up. We'll get to a place where we can just have you guys. It's just algebra's boring, isn't it? Just tedious. Okay, so let me do a little bit more algebra, and then we can have fun. So I've got u plus 1 times x squared du, and then this is going to be 1 minus u squared times x dx. So what am I going to do? I'm going to divide both sides by 1 minus u squared. Is that it? So, and divide both sides by x squared. So this becomes u plus 1. Oh, I guess there was some wishful thinking. I wish it was u plus 1. That makes me sad. It's okay. That's the problem with just making up something. I knew it was homogeneous, but I didn't realize that this was going to happen. Okay. Well, let's pick someone to deal with this because I don't want to have to. Madison, which of these, do you want to do the left or the right? Okay, so what happens over here on the right? Yeah, he's 1 over x, right? Yeah, very nice, very nice. So let me write this down, and then we'll find someone else, another volunteer to help me out. Okay, very nice. And so we're integrating, aren't we? We're integrating both sides. Integrate, because this is separable. It's nice. Okay, let's find another volunteer. Tyler, what do you want to do? Do you want to help me deal with the left, or do you want to just do the right? What, huh?
The left, or I guess I'll just do the right.
Natural log? Yeah, that's right. So natural log of the absolute value of x. We'll put the plus c over there because that's usually traditionally what we've done. Okay, that leaves this. Here we go, u plus 3 over 1 minus u squared. You know what? I feel like I should at least help you out a little bit by factoring this. So here, I'll do that. U plus 3 over 1 plus u times 1 minus u du. How's that? Does that help out any? Okay, so let's see. We'll randomize again. Oh, he's not here. I'm sure he would know. I guess I'll do it then. Well, no, seriously. Does anyone have an idea? You don't have to do it. Just, do you remember what technique? You know? Partial fractions. No. I know, it's like the best.
I'll see you guys next week.
No, we have to. We're going to have to deal with this sometime because it's going to be something that comes up pretty frequently when we get to Laplace transforms. So we might as well deal with it now. So yeah, it's Laplace transforms. There are tons of partial fractions. So that's not until after spring break. You're going to be able to rest up before we hit that. So let me just remind. I'll remind. Don't worry. There's an easy way out. Don't worry. So here's how this is going to look. I know, it's so exciting. And then you multiply, do the cross multiplying or whatever, so that we have u plus 3 is a times 1 minus u plus b times 1 plus u. So just in case, I don't want to make it look like it's easier than it really is. What we're doing here is we multiply the entire equation by that common denominator of 1 plus u times 1 minus u. And of course, when you do that, on the left, that whole denominator goes away. On the right, this one, the 1 plus u will cancel, but you're left with 1 minus u. And here the 1 minus u cancels, and you're left with 1 plus u. Okay, now, here's the cheater way of doing this. Yeah, I know. I don't know if, well, I might have shared this when, I don't know. But anyway, here's the cheater way, is you say, I don't want to have to solve this algebraically. Too hard. So what I do is I do this. I say, hey, what if I just let u equal 1? Then I get 4 on the left is equal to 0a plus 2b, right? I mean, if u equals 1, then this is 2, this is 0, this is 4, right? It's all correct. And so that means b is equal to 2. And then, you know what? We could do the same thing, but we could let u equal -1. Why not? We're going to be doing this a lot, by the way. So this will give me -2a plus 0b. And that gives me a is equal to -1. So there's my a and b. And now we'll just go up here and we'll say, oh, well, that's easy. This is -1 over 1 plus u. And then 2 over 1 minus u. Oh, I read that backwards. Thank you. Thank you. Yeah, it just switched in my mind. I had u minus 1 in my head. It's 1 minus u. Thank you. Yeah. So yeah, sorry about that. It's 1 and 2. So +1, I'll just get rid of the plus there. It's annoying. Okay, and then, so now what that means is that is what we're actually integrating. So we'll integrate 1 over 1 plus u plus 2 over 1 minus u du is natural log of x plus c. And now I'll bet you can do this. Okay, so I know that this guy, he would have been able to do it, but he wasn't here. But Joshua, do you know the antiderivative of 1 over 1 plus u? Now, did you agree with this particular antiderivative?
Yeah.
And so if I just put a +1 there, wouldn't that just change that to a +1?
Yes.
Yeah, so let's just do that. So 1 over 1 plus u should be natural log of 1 plus u. What's that? Okay, what about the 2 over 1 minus u? What's the antiderivative of that? Let's see. Claire, do you have any ideas of that one? Nice. Okay, so -2 natural log of 1 minus u. And all of that should equal natural log of x plus c. Now we just have to remember, what was the substitute? What is u? Where'd it go? Oh, there it is. It's right there. So that means u is equal to y over x. So I know it keeps shifting things around. So we have natural log of 1 plus y over x minus 2 natural log of 1 minus y over x is equal to natural log of x plus c. Okay. Now, I am so tempted to do the algebra. Okay, I will hold back a little bit, but I just need to point something out. And that is that we have these rules of logarithms. I got to write them down because these are going to be super useful. That's one of them. You remember this from the olden days? Like pre-calc? And then this one, There's another one. You remember this whole business? I know. And so you could combine all this stuff. In fact, I will. But yeah. So it would look something like this. You would have 1 plus y over x on top of this fraction. On the bottom, you would have 1 minus y over x quantity squared, because that 2 there can go inside. And then I might as well bring this over so it can join the fun. Exactly. And so now I've got natural log of this ugly thing is equal to c. You could just say all that ugly stuff is equal to e to the c. And that gets rid of the natural log, and e to the c is just a constant. So yeah, we could manipulate this some, but that's not really part of what we're doing. Well, it is sort of. What I want to make sure that we see is that we can do this substitution. It's so beautiful. Okay, we have another substitution though before we go. The other substitution is called, it's Bernoulli's equations. So here's Bernoulli's equation. So, down through history, different mathematicians have bumped up against these differential equations, and they study, and just in whatever they're studying, and then they say, hey, I keep hitting this type of differential equation. Let's see if I can just come up with an easy way to solve it. And so this is one of those, and it's a pretty easy solution to explain. So here's the substitution that we're going to make. Is anytime you have a differential equation like this, dy over dx is equal to some function of x times y plus another function of x times y to some power. That's the key, is that you have that. Anytime you have something like that, you can make this substitution, that is u is equal to y to the 1 minus n, and that will reduce the whole thing to a linear equation. So let's demo this. It's not that hard. Oh, just to show you, no, we don't want to do that. Yeah, let's just demo it with this. Might as well just jump into it with this. Okay, so let's go. I'm going to be toggling back and forth just so you can see this. So what we want to do is we want to take this thing and see if it fits this criterion. Does it look like this? So it doesn't currently. We're going to have to do some algebra, as is the case with a lot of what we do here. So here's the algebra. We're going to first of all dy over dx, expand this. Whoops. Sorry. Oh, come on. So we have x, y to the 4th minus y. Okay, so that's fine, right? Next thing I'm going to do is I'm going to move the single y, the y that's all by itself, move it over to the other side. dy over dx is equal to, oh, sorry, I just said I was going to put it on the other side and I didn't do anything. Plus y is xy to the 4th. Now let's go ahead and see what we can do from here. So going back, here's the substitution. U is equal to y to the 1 minus n. Oh, first of all, notice I have dy over dx. I have a single y times, I don't care what's here, just as long as it's just x. It could be natural log of x. It could be x to the 5th, whatever. And then I have my function of x times y to the n. So here, n is equal to 4. So here, n equals 4. And so the substitution will be this. So that's the substitution we're about to make. And I've run out of room, so it's going to take me a minute to just switch over here. I know every time I do it, you'd think I could learn to not even use PowerPoint. Come on, there it is. I love being able to scroll, infinite scroll. Okay, there it is. Okay, so u is y to the 1 minus 4. So what's that? U is equal to y to the negative 3rd. That's not bad. Okay, so now we need to figure out what our substitution is. So we have du over dx is equal to negative 3 y to the negative 2 dy over dx. Okay, so let's see, does this really work? Where am I? Oh, there it is, sorry. Well, let's give it a go here. So I'm going to take this thing. Yeah, the way I've written this is terrible. I'm going to have to zoom out for a minute. Let me fix this. dy over dx plus y is equal to x, y to the fourth. Okay, so in this case, I'm going to do this the way that I would do substitution. You know, remember in calculus how I was always insistent that I have this, I want to make this appear somewhere. So that's what I'm going to do. And so I will just, I will put it right here. Negative 3y to the negative 2. But I can't just do that unilaterally. I have to multiply everything by that. And so everything, you multiply all the way through. I guess I can do it like this. So let's see what happens. Negative 3y to the negative 2 dy over dx minus, give me a sec here. What's wrong? Did I mess up the derivative? I messed it up? Which one?
Isn't it supposed to be negative 4?
That's such a rookie mistake. I can't believe it. Thank you. Yeah, you got to let me know ahead of time. Otherwise, I'm going to go through all this work. And you're going to be like, Yeah, sorry. Yeah, that's so rookie. It's so terrible. So weak. But anyway, okay, I'm multiplying through now. So then the next thing is going to be negative 3y to the negative third is equal to x times negative 3 y. Oh no, there's no y. It all cancels, doesn't it, over there? I probably should have, let me make sure. So this times this is this. This times this is that. Okay. And then this times this, the y to the fourth is going to cancel and it's up to this.
Is there too many negatives between the first and second term?
Yeah, you're right. I guess I got excited and then got distracted, and then you're right. That should be a plus. Anything else that I've blown it? Yeah, it's time to go. It's time to go home, apparently. Okay, no, we're almost there. Okay, so it's like magic. Look at how things canceled. Now let's actually do the substitution. So I've got u is equal to y to the negative third. That's right there. This is going to be negative 3u. I've got this mess is right here. So that's du over dx. And that's pretty much it. Yeah. Now this is a linear differential equation. Notice that you have this. So it's completely linear. So you can use your linear. So go to your test and you can check to see if you got it right. And if you didn't, you need to learn that I think most of you were using r instead of mu. I used mu. It doesn't matter. But whatever your integrating factor will be e to the integral of whatever function is here, dx, I guess, in this case. So r is, in this case, e to the negative 3x. So I've got du over dx times e to the negative 3x minus 3e to the negative 3x times u minus 3x e to the negative 3x. And now I'm going to be sad once again. But we can overcome our sadness and grief, can't we? So we're going to integrate both sides with respect to x. So if we work together, we're going to be okay. On the left, because this was linear, you know the deal, well, most of you, because you did really well in the test, that once you find your integrating factor, the antiderivative of the left side is just going to be that thing, whatever that is, times your dependent variable. So I know none of you, well, maybe not none of you, not many of you wrote this down like this, but most of you just went to this. You're like, okay, there's my integrating factor, so whatever this is, it's going to just turn into that. Great, that's fine with me. On the right side, though, not as happy a moment when you see that. So do you know what method we're going to use? I know, this is like a review of all those integration methods from Calc 2. So what do you use here? It's not substitution. I'll just tell you that right up front.
Pain.
It's what? The Payne method, yes, it is the Payne method. Yeah, but it does start with P and A. PA, parts. Oh, you love parts, don't you? So parts, this is the one where you let U equal UV minus, yeah, that whole thing. Here, let's go review. It's good review. It's going to be okay. 3x, e to the negative 3x. It's okay. U is equal to negative 3x. dv is equal to e to the negative 3x. Better yet, let's put that 3 with the dv. I think that's going to make things much nicer. That better? So du, let's go ahead, find our volunteers. So, oh, you're not here, but Asol, you know the derivative of x, don't you? It is just 1, very good. So du is equal to 1 times dx. And then, Adric, do you know the antiderivative of negative 3e to the negative 3x? E to the negative 3x, is that what you said? I think I heard the e to the negative 3x part. Yeah, so here's the easy way to double check or to think about this. What's the derivative of this? The derivative of this is that. And so we're good. So yeah, e to the x is both the best function and the worst because it's confusing the way that it's so simple. It's like so simple that it should you think it should be harder. But yeah, that's it. Okay, now I just do this. So it's u times v minus the integral of v du. And so this is going to be x e to the negative 3x minus the integral of v e to the negative 3x dx. So that's v du. Okay, almost done. So that's going to be x e to the negative 3x plus 1/3 e to the negative 3x. The integral of e to the negative 3x is e to the negative 3x over negative 3. All right, so that goes up here. Where is it? X e to the negative 3x plus 1/3 e to the negative 3x plus c. One last thing we got to do, and that's to go back to y. Where is y? Where's the substitution? There it is. There's the substitution. U is equal to y to the negative 3rd. So that's simple enough. Also, I think it would be easier if I multiplied everything by e to the negative 3x. So I could get rid of all of these e to the negative 3x's. So I will do this. Y to the negative 3rd is equal to x plus 1/3 plus c e to the negative, or to the positive 3x. So I just multiplied everything by e to the 3x, and that put that over there. And then, of course, you could solve if you really want to. You'd end up with y is equal to the cube root of 1 over all of that mess. There it is. All right, so I know it's really overwhelming because what I inadvertently, because I just made up a few of these, inadvertently brought in integration by parts and integration by partial fractions, but it's good to be reminded. Your homework, you have just those two. There's another substitution method in this chapter. I'm just going to let it go. This feels like enough. There are, just to introduce the idea that it is possible to substitute and make your thing work. So there's a little bit of time left if you want to stick around and talk about your exam. If you need another sticker, they're over there. And once again, thank you so much. I'm sure my wife will be have tears in her eyes. I mean, literally, it's very kind. So let me turn off the recording in case anyone wants to chat. Here we go.